So I hope everyone can see my screen. Good morning, everyone. I'm Dr. Owain Kenway. I'm the head of research computing here at UCL. But I'm not really here on behalf of UCL. I'm here on behalf of this other organization of which we're part, which is the Materials and Molecular Modeling Hub. And that is, of course, a consortium of a number of universities. This first slide has what I like to describe as the race car slide. It's got all the logos of everyone involved. And as you all know, we're a consortium that does materials modeling, and we run a national service called the MMM Hub. And now I need to get my mouse onto the right screen. So what are we doing today? So today we're going to talk about an expansion to the Materials Molecular Modeling Hub service, Young, that we have purchased on behalf of EPSRC. We've got a fairly varied program today. So between 9 and 12, there's the first section of the event where the various technology partners and UCL are going to talk about the new system, what kind of software it will come, what it will have on it, what you can expect. So in the morning, UCL and HPE and NVIDIA are giving talks. NVIDIA will then give some talks about some of the tools they have available on the cluster. And then in the afternoon, we're going to have a second session chaired by Filippo from NVIDIA, which is going to talk about applications that have been ported to GPU and some of the experiences people have had doing that. Each of these sessions will have a short break in the middle so that people can recover, because we all know that Zoom and Teams meetings can be long and tedious and painful otherwise. So my co-host for the first talk is here, so that's good. The first talk, we're going to talk about the news, what we've procured and why. Myself and Nick Southern from HPE, who is the solution architect who helped us design this system. And we're going to go over why we've made what is, I think, quite a radical departure for the materials service from what we've done up until now. Kind of the benchmarking that was behind it, done by both parties. And then Nick is going to talk about the system design and go into quite some depth as to what we've built. And then I'm going to explain what it's going to be like when you log in and what tools and services we have available. So why are we doing this? So why do we do this at all, in fact? We provide the Materials Hub service because we want to provide a computer that's useful for materials researchers. And that means that when we go to when we decide to build a machine, we don't look at building what is the most interesting service to us. We want to build a reliable, boring machine that runs your software very well, right? The exciting thing that's happening on the service should be your science, not the computer itself. And so what we do is we do a survey of the existing services, of what codes are being run, and then design a system that is optimal for those applications, right? So we're not trying to get a top 500 benchmark. We're not trying to make an exciting ARM and FPGA system. We're trying to build a system. We're trying to build a machine that will run your code the best. And so consistently throughout the lifetime of all the services, we have found that the top codes are VASP, LAMMPS, GROMACS, and CP2K. This has an impact on what we buy, because up until relatively recently, only some of these codes had any GPU support at all, never mind good GPU support. And so certainly when we tendered for Young originally, when we bid for the money for Young in 2019, there was some very nascent support for GPUs in VASP. But it was largely not useful to people. LAMMPS had a GPU module, but it required some fiddling about with input files to get to work. And to get it to fit on GPUs, you often involve changing the science you're actually doing. GROMACS of the codes had the best GPU ports, and demonstrated really strong performance. And CP2K had some porting, but not a lot. But the end result was that when you're looking at building a whole system, you have to make a trade-off between the applications and how they perform. And so it made sense to buy a CPU-only machine, because that was an effective architecture for all these applications. It wasn't worth buying a small GPU section just for GROMACS users, right? Because you can't guarantee, although they are a significant portion, you can't guarantee you're going to get the same proportion of usage all the time. But of course, time has trickled by, and it's now a few years later. In that time frame, we've had a refresh of the UK National Service, which is a machine called Archer 2. And that has been an interesting experience, I think, for some of the research groups at UCL, because it turns out that VASP, which is our most used code, and it's the most used code on the Materials Hub, so across all those partners as well. Certainly for the workloads our people are running, is not performing on Archer 2 like what would be expected from the architecture, what we'd hope for. And we have some theories as to why that is happening. Some of it is, so Archer has a very high core count per node, and it has AMD processes where the per processor memory bandwidth has gone up, but because it has more cores, the per core memory bandwidth has gone down. And we know that the VASP workloads people use really push, are really dependent on memory bandwidth, so that throttles performance. The VASP is one of these applications that's very optimized for Intel's processors because they have been the primary HPC processor for the last decade or so. It actually is one of the codes that makes use of the wider ADX512 instructions, which are not available on the AMD chips. And there are other things that kind of strangle memory performance as well in the architecture. So Intel processors have a thing called a QPI link between the sockets, which allows faster memory transfer between the processors. That's missing on the AMD cores, on the AMD processors. They have more complicated memory architecture, more complicated NUMA, and that can have all kinds of side effects for performance. And what was discovered by one of the teams here, who I'm going to keep referencing David Scanlon in this talk because his group has been really helpful in kind of informing how we design this future machine. They were finding that running on Young, which was a few years old, at that point was a year or two older, was almost twice as fast per core as it was running it on Archer 2, which is a problem for them because they were expecting an upgrade in performance, right? At the same time, NVIDIA spent a lot of, I suspect, money and effort convincing the VASP-6 developers to work with them to get a GPU port of VASP, which was actually performant. And that work had been done. And so armed with these two bits of information, we set out to work with HPE, who are the hardware provider for Young, to work out what we would buy for UCL's use, not necessarily for the MMM hubs, what would be the best way to run VASP in future, right? So we have two processor architecture options, there's AMD and there's Intel. We have, are GPUs useful? So we did some work, like essentially co-design, right, with the team at HPE. David Scanlon's group provided real input files with, real workloads. And these were run on test systems at HPE by HPE's benchmarking team. And Nick will talk a bit about this work later on in the presentation. We also did our own benchmarking because we like being thorough. And we have a different service from a different vendor called Myriad, which is not even really targeted at the same type of HPC. This is a machine that's intended for what we call high throughput workloads, so it only does single node jobs. It does very data intensive workloads, so it's got very fast connections to storage. But what it does have is a variety of different node types, including nodes with very large memory of order of about 1.5 terabytes, and also a variety of different types of GPU nodes. And we had just procured, as of last summer, a number of nodes which had NVIDIA's, what is probably the worst GPU configuration for this, right? It has 4 A100s connected through PCI Express, only 40 gigabytes of RAM per card. But we thought it was worth doing some of our own benchmarking. So we have built up VASP 6.2 and 6.3. One of the interesting things that is happening is that it's quite clear that NVIDIA and the University of Vienna are working actively on this because each successive version has more support for GPUs. So it's clearly getting even better as time goes on. We built them up with Myriad. We built up the corresponding CPU builds on Intel, on the Intel compilers. I will talk a bit about the NVIDIA HPC SDK later on in the talk. And we put them on Myriad, made them available to users, and got David Scanlon's group to do some benchmarking. Their standard test system is hybrid functional DFT in a 64-atom magnesium oxide supercell. And that's about where my knowledge of this particular bit of science ends. I'm afraid I'm an IT person. But we have essentially 3 test systems, right? We have the nodes in Myriad, which are 4 times PCIe A100s. We have the CPU nodes in Young, which are 40 cores per node, Cascade Lake, with OmniPath in between them. And we have Archer, which has 128 cores per node AMD using the Slingshot interconnect. And based on their benchmarking figures, a single one of those Myriad GPU nodes is about equivalent to 440 cores, so 11 nodes of Young in performance. And on the other side, in comparison to Archer, a single A100 Myriad GPU node was about 1,024 cores worth of compute. The main caveat there being that because their workloads are very memory intensive, this is only true until you run out of memory on the GPUs. And there's much less memory on 4 A100s than there is in a node, in 1,024 cores of Archer compute nodes. And at that point, you have to choose less optimal parallelization and scaling, and so it performs less well. So special thanks to Bonan Zhu and Sean Kavanagh from David Scanlon's group for doing this work, because it's been really helpful in informing what we do as we go forward. On the back of this and the work HPE has done, we decided to bid to build an add-on to Young that would help materials researchers move on to doing stuff on GPU. And there's some other motivations for this. I think it's fairly clear if you look at the exascale Pathfinder machines in the US, they are all accelerator based, so GPUs of some variety. We need to, if materials codes are predominantly CPU, the community is going to have trouble getting access to national resources in future, because future machines will be accelerator based. So what we wanted to do was put together a system and a set of training and a program of events to help upskill materials code developers and users in using GPU systems. So when EPSRC announced a call on the 5th of October last year, we bid for 750K worth of hardware to purchase GPU nodes for Young. And we based this on the design we'd done with HPE for our own service, Kathleen, which ironically did not get funded internally. So this is the first machine of its type at UCL. And we also bid with a lot of people skill support from Cray and NVIDIA, so that we would have people to help porting and optimizing codes. Because although these processes are much faster, the characteristics of them are different, and the characteristics of what is the optimal job shape is different. And obviously there's the issues of porting existing codes. This was an extremely challenging bidding process. EPSRC announced the call on the 5th of October with a deadline for the 25th. So for those of you who are almost as good at maths as me, that's 20 days. Worse, my co-I Scott Woodley had COVID, so we were struggling pretty much the entire time. We had an incredible amount of support for so many people, both in the MMM Hub and at UCL and at HP and NVIDIA. It's really, this would be an endless slide if I listed all of them, but obviously Scott Woodley and Arash from Imperial were instrumental in helping getting the academic case together and kind of marshalling the academics. 2 people who do a thing that I think is not shouted out enough, actually, in delivering these systems. We have a person called Christopher Langridge, who is the departmental administrator, and his expertise is pushing the levers of research bureaucracy to get things done. And that means helping sort out with Work Tribe, we're helping sort out JES, badgering people further up the chain to actually approve things on time so that the bid goes out. All these things, and this would never have happened without him. Dan O'Keefe is what we call in UCL an agile delivery manager, which is a sort of agile process version of project manager. And the other side, in the actual delivery of the system, he has been tireless and very effective at getting the thing delivered on time. And again, when we talk about the systems, we often talk about the technical work that goes on, but a very big part of this process is paperwork, right? And these guys have made this actually work. Without them, we would not be here. Similarly, Eric and the team at HPE have done a really sterling job, both in getting the design ready for the bid really quickly, and on delivering the hardware, getting it prioritized within HPE, because HPE is a massive organization with a lot of customers, and these are big, complicated systems with a lot of parts. And getting those through the supply chain, getting those built, getting that on site is a really challenging task, and they've done a really good job. And Filippo from NVIDIA, who has been really good at marshalling NVIDIA to get support for this, to get, even organizing today. So Filippo is having some issues, I think, getting on Zoom, but at the moment, this is all his work, organizing this. So I want to thank all these people. These are not the traditional academic or tech side of this. This has been a really good grunt from everyone, and it's been really, really sort of satisfying to see that everyone has pulled so hard to do this.